Hi, we are Team Gold, Group 17, and this is our Project 1 presentation for mechanical design, including 5 parts to be analyzed for force and moment distributions throughout the small pocket knife we have shown here. Here we have the exploded view of our part. This nice photo of our design will serve our purpose of identifying what components each of us studied. One important factor is to denote that we broke down our knife to be utilized using one knife to be flipped open. Therefore, the following presentation is in relation to the left-handed side of the knife. Everything we discuss could be equally referenced to the right-handed side, but since the two sides don't affect one another, we decided to simplify our analysis. We have discussed how our loading, due to our hand, was transmitted between each of our parts and were referenced by their static and dynamic forces.
No.
We considered our part as a whole entity when listing its applications, manufacturer, and source. My part, the steel frame, provides stability for the knife to function and flip open. The greatest force for the steel frame is on the inner integrated rods of the frame that limit full rotation of the blade when force is applied. The knowns and unknowns are few and will be further addressed in the free body diagram, but they are expressed with relation to an individual holding the knife in an upright position and when the blade is fully extended outward as a result of the user flicking it outward. The manufacturer is Tech Sports, and our product can be used for tactical and personal defense and for personal use with regards to being a novelty package opener. My steel frame, through research, has an elastic modulus around 200 gigapascals, a yield strength of 215 megapascals, and an elongation at break around 70%. Our item was given to us because it was given to Yadira as a gift, and we took advantage of the fact that she was readily prompt in providing said item. Here displays my component with the use of Yadira's tablet drawing capabilities and my drawn out representation of the frame addressing the known dimensions. Fx in the frontal view is the force of one's grip, which is an external force applied on the knife, and mass and gravity are also deemed to be known forces. The top view contains the reaction force Frz due to the blade and the normal force Fnz, which is the force of the rod pushing back against the blade at contact.
This next section is over the essential component to holding the system together, the pin. When thinking of a pocket knife, most would conceptualize something along the lines of just a handle and a blade, but in reality what allows pocket knives to stay in place or fold up and secure the blade is the pin. Without it, there would just be unconnected parts with no relation to one another and nothing actually put together. With the way our group has plotted the system on the axis, it is observed that the pin rotates along the x-axis and is shown in the free body diagram slide. Through simple research, we found that the pin is made of 6061 T6 aluminum that is coated in black. The elastic modulus is 68.9 gigapascals. The tensile strength is 276 megapascals, and the elongation at which the material breaks is 12%. Here is the breakdown of the dimensions and each of the forces involved with the left side pin. From the side view of it, we can observe that there are 3 equal and opposing forces that are acting on the pin and the z-axis, which are labeled as Fz1, Fz2, Fz3, and negative Fz4, negative Fz5, negative Fz6. With the negatives on the Fz4, 5, and 6 because they are the reacting forces from the frame due to the contact points. The top view of the pin shows where there's a moment acting on the pin in the counterclockwise direction, because that is the direction the knife blade swings when opening the knife. We also include that there is a normal force acting upon the pin, as well as gravity. The forces that we know are the mass of the pin, gravity, and according to your statement, external forces and moments are known as well.
So my part is the outer casing. The function of the outer casing is to provide stability and protection to the whole knife in its parts as the blades. The knowns are the mass and gravity. The unknowns are the normal force, the force in Y1 and force in Y2. and the material that is made of is black coated 6061 T6 aluminum. The elastic modulus is 68.9 gigapascals, the tensile strength 276 megapascals, and the elongation at break is around 12%. So the forces that are known are the normal force and the gravity, and the other forces that we do not know is the force at y1 and the force at y2. The dimensions of my part of the other crazy is the height is 17.81 millimeters. It's 83 millimeters long.
Now we go into the blade. So the blade is a part that has the ability to cut or slice objects. For the knowns, we have Fx and we have Fy. These are the forces that are applied by the person. And for the unknowns, we have the moment at C and F of x2. It is made out of steel. Steel has an elastic modulus of 200 gigapascals, a yield strength or tensile strength of 250 megapascal, and an elongation at break of 70%. If you look on the left, we have F of x1. This is a force that you applied into the blade. When you apply that force, you're going to have a force that's going to come from the steel frame. This is force F of x2 in the right. Also, you're going to go ahead and apply a force Fy, and when that happens, the blade is going to go ahead and unlock, causing a moment in the C direction, MC. The blade is 65 millimeters long, and it has a height of 22.5 millimeters.
The next item we'll be talking about is the spring. The functionality of the spring allows the blade to rotate along our x-axis, and at the same time as it's rotating, it allows the blade to stay in place when it is open by applying a tensile force onto the spring. The spring also allows the blade to be closed completely and remain closed as it rotates in the opposite direction, which depends on which of the sides of the blade we are viewing. The knowns of the spring we found are its mass and gravity that act upon it, but I'll talk about the unknowns when we see the free body diagram. The application, as mentioned before, is a novelty, a handheld item from Ice Tech Sports, used for personal and tactical use with a cost of $14.20. And the material that the spring is made out of is steel with an elastic modulus of 200 gigapascals, a yield strength of 250 megapascals, and an elongated break at 70%. As we take a look at the free body diagram and our sketch of our dimensions, we can see that the spring has two knowns that we were able to identify, like I mentioned before. The mass and gravity, as far as the unknowns, we have two tensile forces, each acting away from the center point, this occurring as we either open or close the blade. There are also forces named Fy1 and Fy2, which occur when the blade opens or closes as it's met with the wall of the entire blade's casing. We also find our normal force that acts on the spring, because when the blade is closed, the spring lays on the bottom part of the Batman casing. And as we further examine the spring, we note that the end of the spring, which is used to insert itself onto the blade, has a clockwise motion that occurs as the blade opens, and a force in the z-axis, Fz1, also occurs when the spring falls into the blade hole. To conclude, we took the cost of the design in its entirety based on the price of the manufacturer and found all its mechanical properties according to the ASTM standards. We considered identifying the forces and the moments that were transmitted to each component to be pretty difficult, especially when each component is related to one another at different states, either in a static state or a dynamic one. Addressing the reactions was not as difficult to understand. However, the challenge was perceiving the forces and what directions they took. In all, the project was a difficult one because you had to analyze what one force can do to an entire device.